Good day, everyone. Welcome back to Understanding Digital Electronics. Today we'll be looking at the fundamental building blocks of digital electronics, which is logic gates. Before we cover that, let's go back to talking about binary. On last video, we discussed how binary is basically like the decimal number system, except it only has two values. Well, now, when it comes to logic gates, we're going to treat this binary not as a number system, but as a signal. Logic gates basically act like an electrical circuit. In your computer, you'll have things called, your computer will do calculations and all these sort of things. And basically, how that's facilitated is through a transistor. And without going too much into the details, a transistor is basically a switch that goes on and off depending on a signal. Now, basically, binary is that signal that switches on that transistor or not. And when we look at binary, we have the two numbers, 0 and 1. 0 is called an off state. This is off. So when we have a 0, it means we have no power or no electricity. So if we basically connect a lamp to something that has a 0 signal, the lamp won't turn on. But now, if we take a look at this, the 1, this is our on signal. It means there is power. So if we connect a lamp to a 1 signal, then the lamp will turn on. And that's how this is going to work with logic gates. And this is basically going to turn on or off a switch. So let's take a look at the most simple sort of gate, which is called a NOT gate. A NOT gate is basically represented like this little arrow, and then it has a dot on the end and there. This dot represents that it's a NOT, that it's an inverter. Well, what does that mean? Let's take a look at its electrical circuit. I would draw this. This is what we call a normally closed switch. Normally closed. So current just runs through this without a problem. But the second this contactor gets powered, so the second we apply a 1 to here and not a 0, this contactor opens and the current is cut. But when we bring it back to 0 again, then the contactor will open and the current is allowed to flow. And this will then make its way to our output state. And we can then draw this in a sort of table called a truth table. If our input is A and our output is B, then so this switch by itself is the NOT gate. So when I apply an input of 0 to this switch, this normally closed switch, well then it's going to remain closed, and that means the current's going to flow, so we're going to get an output here, which means if we have an output of on, well, we're going to get a 1. But now when I switch this back to being 1, what happens? It opens up again, and then there is no power coming to here. So when I have an input of 1 to this gate, well, there'll be no power output, so I get a 0. And we can represent these signals by we can represent these signals on a timing table. So if this is my B signal, and this is my A signal, I can run any sort of signal, but I'm going to do 0, 1, and my signal is going to start low, it's going to go high, and let's say I just put 1, 0, 1. You see, I'm just feeding this a constant string of information, right? That is my input signal. The output signal will be, well, this is a NOT gate, so when that's 0, that's 1. When that's 1, that's 0. When that's 1, that's 0. When it's 0, it's 1, and so forth. And then when we draw out our output, it's going to go above, below, above, below. And that's basically what it looks like. And now there's something that we will go further into in the next video, but I'm going to give the brief overview while we go through this, is A is equal to not B. This little bar here is the same symbol as that. It indicates that this is not B. So A isn't equal to B, it's equal to the opposite of B. So if A is 1, B is 0. Okay, now that's the simplest gate. Let's look at a more complicated one. We have something called an AND gate. Now, when you look at English, or when you look at probability actually, the term AND means two events have to happen at the same time. Let's look at the symbol. The symbol for an AND gate is this curled this. And you notice here that there is no dot, meaning it's not going to be an inverter. It's not going to have a normally closed switch. So this is our A input, our B input, and our C input. And when we go to actually think about this, we need a circuit that requires event A to be on and event B to be on to give an output of on C. Because A and B need to happen. So when we go back to thinking about circuits, that means they have to both be in series. And instead of being normally closed, these are normally open. And what does that mean? Well, it's the exact opposite of a normally closed. This will remain open when we have a 0. When it's 0, it's open, no current's going to flow. But when this becomes 1, well, current's going to flow. But you notice the current's actually not going to flow. Because where's the current flowing to? Is it flowing to another open circuit? So what needs to happen for both of these to be closed is this needs to be a 1 and this needs to be a 1. And then we'll get an output of 1 here. So the way you draw this circuit is it's a normally open with just the two parallel bars. So these switches need to get powered to close. Well, that looks like normally closed. So when we take that logic and we put it in our truth table, this thing, we're going to have two inputs now though. So we have our input A and our input B. And we have our output C. And when we look at this, we're going to say, well, if A is 0 and B is 0, then C is going to be 0. Makes sense? And then we're going to say, well, if A is 0 and B is 1, well then C is going to be 0 because we need both of them to be closed. If A is 1, this is 0, B is 0, then this is going to be 0 because we need both of them. And finally, we're going to look at 1, 1, when both A and B have a signal of 1 going through them. And that's when we'll get an output of 1. And this can work with as many inputs as you want. So if we have 3 inputs, it'll only work when A, B, C are all 3. I mean, are all out 1. And your truth table will have 7 zeros and 1 1. Now, the number of possible combinations you have. So you see here we have 4 combinations. We have 2 combinations, 2 different input states and output states. So here we have 2. Well, that's based on just the number of inputs you have. If I have an input of 1, I mean a 1 input only, then I'm going to say 2 to the 1 is going to be my total number of possible combinations. And it's just going to be 2. Now if I look here, I have 3. I have 2 inputs. So I'm going to have 4 outputs. Because that's just 2 to the power of 2, which is equal to 4. And if we have 3, we'll have 8 outputs, and all these sort of things. Now, let's look at our timing diagram. We're going to redraw this now. We're going to say C is at the top. We're going to say A and B. Now, if A is 0, B is 0, A is 0, B is 1, A is 1, B is 0, this is 1, and this is 1. Now we're going to draw this. We're going to draw our timing diagrams. Now, we can basically look at this and say both low, that's going to be low, low. The second we see a single low point in the diagram, we'll just write 0. I don't even need to check the state of B in this case. The second I saw that low, the second I saw the low in A, I know I'm only going to get a low output. And then I put on the final one because this is high and this is high. And there is my timing diagram. Now, when we go back to the algebra here, well, what is C equal to? C is going to be equal to A and B. Because if A is 1 and B is 1, we'll get an output of 1. But we know in normal maths, if we times anything by 0, we're going to get an output of 0. So that's why our formula for an AND gate looks like that. Now we're going to go into the next sort of gate, the OR gate. Once again, if you look at probability, it's the probability of one event happening or another event. So there's 2 different probabilities, and you can add them up together. And that's also, when you look at AND and probability, it's one event times the other event. Now an OR gate has a slightly different symbol. Instead of this flat curve LED look, it has this sharp point. Also notice there is no inverter there. And this is our A input and our B input. This is our C input. Now, for us to have an AND, we needed them to be in series because both events needed to happen in order to get a powered output. Well, for OR, we need to look at a different sort of thing. Instead of thinking of in terms of series circuits, an OR gate is more like a parallel circuit. Because even if I don't have any power coming in through here, I have power coming in through this side. And I'll get an output here. And both of these, because we don't have an inverter, that's normally open and that's normally open. We can now look at our diagram and we can just base it off this, as I'm sure you can start to see now. So if I have an A, a B, whoop, B, a C, well, we're going to go here. Whoop, sorry, that's supposed to be a 0. We're going to go like this. Now, when both are 0, there's going to be no power going through there, so we're just going to get a 0. But now, when power goes through B, well then, there must be a 1 because current can flow to the output. And here also. And now here is where people might get confused. Well, oh yeah, well you see, we have a 1 and we have another 1, so we get plus, so we must get this. That is wrong. And this is where you have to separate binary, the number system, from binary, the signal. Because 1 plus 1 in binary, the number system, will give us 1, 0. But binary as a signal, if we have current flowing through the one side and current flowing through the other side, yes, there will be more current in the branch, in the output, but it will still be powered on. So this isn't looking at how much is actually there. It's looking at, is it on or is it off? And even though we have 2 on states, which means it's going to be on. I'm not sure if I explained that properly, but let me maybe make it a bit simpler. We're not trying to look at the amount of actual current going through there. We're basically looking at, is the lamp on? Yes. Then we're going to put a 1. Is the lamp off? Yes. Then we're going to put a 0. It doesn't matter. You can plug 2 wires into the lamp, both providing current. The lamp is still on, so we're still going to put a 1 output. And then, if we look at our timing diagram, we're going to say C, A, B, and this is 0, 0, 0, 1, 1, 0, 1, 1. We're going to draw our things. Oh, that's a bit too close. We're going to draw our things. Now, unlike with an AND gate, the second we saw a 0, we knew we were going to have a 0 output because it's multiplying. With an OR gate, when we're adding, well, we just need to see a 1. So here we have 0, 0. Well, that's obviously going to be 0 because no power plus no power gives no power. But now I see a 1. So I immediately know that's going to be 1 because anything plus powered will give us a powered output. Now, I see A is 1 immediately. I don't even need to check the signal of B because A is powered, which means we're going to have a powered output. And there again, A is powered. I don't even need to see if B is powered because I know it's going to be 1. And then we can just go like this. And now, of course, the formula we use for an OR gate is going to be A plus B is equal to C. Now, OR gates can also have as many inputs as you want. You can put 4, 5, 6 different inputs. Also, something I just realized, I made a mistake, I believe, that this shouldn't be not B, it should be not A, because A is being inverted, not B. My bad. Sorry about that, guys. Now, let's begin on another sort of type of gate, an inverted AND gate, which we like to call a NAND, or a not AND. It shares the same symbol as the AND gate, except instead of the just round like that, it also has this dot, which, as we've said with the NOT gate, is an inverter. Now, how do we represent this? How do we draw an electrical circuit for this? Let's first draw our table, right? Since it's going to be a NOT gate, since it's going to be everything A is but, and then it's going to be not that. So our A, B, and C. So this is 0, 0, 0, 1, 1, 0, 1, 1. Now, you would think, oh, it's just going to be maybe, actually, no, cut that part. So now, you look at this, and what was our AND output? Let's go back here. Our AND output was 3 zeros and a 1. So the output we normally get is this, 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 this. But now, what does the NOT gate do? Remember, every time we have a 0, we turn it into a 1, and every time we have a 1, we turn it into a 0. We invert it. Now, since this comes after the AND gate, it means that we're going to take this value. This is what we're supposed to get out of an AND gate, and then we're going to flip it. We're going to invert it, and we're going to get a 1. We're going to get a 1, 1, and a 0. So basically, we've taken the normal output of an AND gate, and we've changed it. And when you're actually going into like coding these sort of things or building them, the way to build a NAND gate is in coding and stuff is you could just normally say AND gate with not AND. So you'd say not an AND gate. Now, your first thought would probably be, okay, well, that's simple. We're going to build the circuit now. We're going to do this. And you see, since there's a not, we're just going to draw two normally close, and there's our circuit. The problem is when you actually look at this, this is still a series circuit. So at 0, 0, this will be closed. We'll get our 1. That's yes. But now, what about when we get a 1 for B? Well, when B becomes a 1, all of a sudden we get a 0 output. So that's not going to help. So if that output's 0, then this can't be our circuit. And same if A is on, going to get an output of 1. So that can't be right. But it definitely needs to have NOT gates because it's an inverter. Well, what we need to look to is the OR gate. Basically, what this does is if 1 is 0 and the 1 is 1, we'll get a 1. So this and this. And if we swap these to normally closed gates, that would still be a 1 and that would still be a 1 because the 1 will have a different state than the other. So we'll still get an output of 1. I'm not sure if I explained that well, but let me demonstrate it. So we're going to redraw this now, and we're going to make this normally closed. And then we're going to put another normally closed in parallel with it. And now, of course, when this is 0 and 0, well, this is closed and this is closed. So what are we going to get? We're going to get a 1 because power is allowed to flow through. But now, just like an OR gate, even though we're now using two normally closed, when this one is powered with a 0, this opens. But this one is still getting current through. And when this one closes, well, that won't allow current through, but this will. So even though we've swapped the gates around, the middle part of the gate will still function the same way. So this will still be 1 and 1. And then when both of these are powered, well, that's open and that's open, so we'll get a 0. So that's what our gate should look like. Not only did we swap the gates out, but we also swapped what type of circuit it is. And now, here's where we'll go into a bit of a understanding of Boolean algebra, where we'll touch a bit more on it now. So the formula for this circuit is A times B is equal to C. That's our AND gate. But then we invert the entire AND gate. Now, as you can see, this gate is now two normally closed gates in parallel. Now, when it's parallel, it means it must be plus. And when it's closed, it must be, if this is A and this is B, well, A is an inverted gate because it's a normally closed, and B is inverted. So this is one of the fundamental concepts of Boolean algebra, is that when we invert something, when we invert a multiplication, so A times B, the entire situation. So we're not saying this is very different to A inverted times B inverted. This is not equal. This is A and B both inverted. And when they're both inverted like this, then we'll get this formula. Now if we go back to our timing diagrams, let's just do a quick look at that. We're going to say C, A, B, 0, 0, 1, 1, 0, 1, 0, 1. And we're going to just draw. You've seen this before. Now, since this is the opposite of an AND gate, when we're looking at our timing diagrams, with an AND gate, the second we saw a 0, well, we just put 0, because we know that anything times 0 give us 0. Now, with this gate, when we said 0, we just immediately put a 1. Oh, 0? I don't even need to check B, because I know the output will be 1. And there's a 0, so I'll get a 1. Now, both of these are 1. I know that has to be a 0. Now, just regarding a bit more of Boolean algebra, I want you to go home. I want you to, at home, try and figure out why this equation works. Plug in your values from your truth table into here and see if this equation does actually satisfy this equation. It's a nice little exercise to do. And now we have our next gate, which is the NOR. As you can guess, this is a not OR. So it's going to be the same symbol, but now with an inverter. This is going to be C. No, that's not C, that's our inverter. This is going to be C. This is going to be A. This is going to be B. This is going to be B. And now, if we go and draw our truth table again, or A, B, C. Well, let's first fill in our values for A and B. 0, 0, 0, 1, 1, 1, 0, 1. Well, if you notice here, right, with an OR gate, we'll only get a 0 when it's here. So the rest of the time, it's going to be on. Only if both are off, it's going to be on. So we want this to be inverted. So we want a power that's going to be 1 when both are 0, and it's 0 when everything else. Now, does that remind you of anything? That only one thing will be powered. If we look back at our original AND gate, only this will be powered. But now, that's when both are 1. If we go and draw the circuit now with normally closed switches, so that's our AND gate. But now if we close them, well, when this is 0 and this is 0, when this is 0 and this is 0, when A is 0 and B is 0, we'll get a 1. There will be power flowing to it. But now, when either of A or B both get powered, the thing will become 0. And now, if we actually look at our Boolean laws again, we can now write the equation for this. You can figure out your equation just by looking at your truth table, by the way, if you're interested. If you don't remember if you don't remember exactly how it is, but you remember your truth table, you can just derive that. And if you know your equation, you can just derive your truth table. So this is going to be A plus B, since it's an OR gate, and then we're going to invert it to get our C value. Now, this is now this is A and this is B, but they're in series. And when they're in series, both of the things have to be multiplied together. But now you notice that A's are normally closed and B's are normally closed. Now remember, this is also not the same as A times B all inverted. It's not the same. Just like this isn't the same as A inverted plus B inverted. It's not the same. And once again, I'll leave it up to you. You can go and work with this, prove that it works, but we'll discuss more of it also in the next video. Now we're going to look at our timing diagrams. C, A, and B. It's going to be 0, 0, 1, 1. It's going to be 0, 1, 0, 1. And then we're just going to draw this. By the way, these were questions that did come out in the exam, like working with your timing diagrams and that. That's why I'm trying to show you why it's important to understand these relationships so you can just quickly look through them all. Now, when I look at the timing diagrams for an OR gate, the second I saw a 1, what did I do? The second I saw a 1 here, I put a 1 as my output. Now, here it's the opposite. The second I see a 1, now, if I see a 0, well, I don't do anything. But if I see a 1, so here I know I have a 1. But the second I see that 1, I know we're not going to have an output. 1, we're not going to have an output. 1, we're not going to have an output. And there is, oh, no, that's the wrong way. And there is our diagram. Now, let us begin on the final two gates. We first have a XOR gate, which is commonly known as an exclusive OR. So it shares a similar symbol to the OR gate, except it has this little gap here, and there's our A input and our B input, and we have a C output. Now, the reason this is exclusive is instead of just being parallel branch with just a normally open or normally closed together, it has this. Normally open, normally closed, and then a normally closed, and a normally open. So this is A, this is A, this is B, and this is B. So what this means is when A gets energized, so when when this becomes 1, well, this will close and this will open. And when B closes, when B gets energized, this will open and this will close. So that sort of combines like a weird AND gate in parallel. So let's take a look at what this truth table will look like when we do it. A, B, and C. Well, if A is 0 and B is 0, well, that one has to be 1. So that one's going to be open, so therefore there's no current going through there. And B is going to be open, so there's no current going through there, so we're going to get a 0. When B is 1 and A is 0, well, A is going to remain closed, but B is going to open here. A is going to remain closed, and B is going to close, so we're going to get a 1 output. Now, when A is 1 and B is 0, well, A is going to close, and B is going to remain closed, so that's going to give us a 1 output, and we don't need to look at the other branch. And then, when we have a 1 and a 1, well, it's going to be the same situation as before. A is going to close, but B is going to open. A is going to open, and B is going to close, so we're going to get a 0. The reason this is exclusive is basically whenever they are the same, you'll get an output of 0. But whenever they're different, you'll get an output of 1. And the way we would write this formula now is A, B naught. So these are terms because they're in series. And then we're going to plus A naught times B is equal to C. And when we look at our timing diagram, well, we're going to get C, A, and B. This is going to be 0, 0, 1, 1. This is going to be 0, 1, 0, 1. So the main issue with this is unlike in previous gates where like um with the NAND gate we just had to find a 1, or the AND gate where we just had to find a 0. This one you have to look at all the combinations. If we have so since we have two inputs, we have to look at both of these inputs to figure out what's going to happen because we need to compare. And when we get our output, this becomes this will become 0, this will become 1, 1, and 0, because these are the same and these are the same. And there we go. This will come more into play in some of the later sections as well, learning to understand some of these things. Now what we're going to do is we're going to go into our exclusive NOR. So this is same symbol as the exclusive OR, but now with the dot, meaning it's inverted. This is A, this is B, this is C. And now let's do this instead of starting with the truth table or anything. Let's take our formula. We know that this is A, this is B, invert, plus A invert B. And now, since this is being all inverted, this is going to give us C. So here I'm going to lay out some more rules of the Boolean algebra. And we can see this in practice here. So, what do we know? We're going to treat this as one thing and treat this as one thing. Well, we know that when this is a plus, it's going to become, this is going to become A times B invert, and we're going to multiply this by A invert B, all inverted. And then we're just going to apply the same rule again. Now we know that this is going to be A invert plus B invert invert. Oh, that's weird. And this is going to be A invert weird, plus B invert. What do we do with this? Well, if we think about it in practice when we have these, right, is, let's say A is equal to 1. Well then, A invert would equal to 0. Now, if we invert A invert, well, if A invert is 0, then we're going to get 1. Therefore, this is equal to this. So we can just, when we see two lines like that, we can just cross it. We can't cross these two because that covers both of them and not just B, but we can cover it here. So what we get is A invert plus B, A plus B. And now we're going to go we're going to now expand the terms. We're going to get A invert times A plus E invert times A invert times A plus A invert times B invert. Then we're going to get plus B times A plus, so this equals C, plus B times B invert. Now what do we know? We know that A invert, A invert must be the opposite of A. So if A is 1, then this is 0. But if A is 0, then this is 1. And you notice a pattern here now. If we are multiplying these, then no matter what situation we get, we're going to get 0. Because there's only two numbers it could be, and one of those numbers has to be 0. So we know then that any times we have A invert times A, we're going to get 0. B times B invert, we're going to get 0. So then our final formula is going to be A invert B invert plus AB. So now we've just used the basic laws of Boolean algebra and what we know so far to change this formula into this formula. We'll cover more of this again. We'll probably cover the same example in next video. So I can emphasize this because a lot of people do get confused with Boolean. Now we have our formula. We can now look at it and say, okay, how do we draw this? Well, we have a plus sign, so we know we're going to have two lines. And then each line will have, I think, so this will be A, and this will be B. And they're going to be normally closed. And this will be open, and this will be open. And now, if we want to also practice with our formula, we can say A, B, C. And practicing with our formula, we're going to get 0, 0, 0, 1, 1, 0, 1, 1. Now, if we plug these values into our formula, we can see that if A is, they'll become 1, this will become 1. So that'll be just 1. And then we know, since this is a plus, we know that if one of these terms equal 1, we'll get a 1 out. That's how OR gates work. Now, if we were to say 0 and 1, well, we know that that must be 0. That'll be 1. That'll be 0. Yeah, that'll be 1 and that'll be 0. So, therefore, that'll be equal to 0. And then this way, well, one of them is 0. So what this basically does now is whenever we have two values that are different, then we'll get a different answer now. And then since they're the same, we'll get a 1. And now, just to proof check ourselves one more time, the exclusive OR has a value of 0, 1, 1, 0. And as you can see, these values are inverted. And then the last thing we need to do is check our truth tables. So this is C, this is B, this is A. Sorry, I flipped them around. This is A, and this is B. This is 0, 0, 1, 1. This is 0, 1, 0, 1. And now, once again, we just have to compare, see, okay, those two are the same, those two are different, and that's the same. The nice thing is, if you're working with one of these that has multiple inputs, yeah, there we go. Now, a key thing to note about these gates and logic gates in general is you might be given a formula, and then you'll have to draw the logic gate. So when they say draw a logic gate, they don't want you to draw this, the switches. They want you to draw this. Now, the reason I drew these is to help you understand why and how this works. Like, on an actual level, what are these doing? But you actually need to know when you're asked to draw, when you're given an equation and then asked to draw the resulting diagram, you need to be able to remember these symbols and add them. So that's the basics of logic gates now. Thank you. I hope you enjoyed.